Hello everybody, and welcome to the second, well, not the second because the high performance people have been going for some time, but last year we had a numerical workshop and we combined the high performance workshops and the numerical workshops. And so I suppose in a way this is the first one. I just want to say, first thing I want to say is a big thank you to someone who's not here as far as I can see, Marco Zocca, who's been instrumental in helping organise the whole workshop, and sadly he's not here. So on the video, Marco, thank you very much. Secondly, great to have Trevor here to talk to us about Accelerate. Well, I'm looking forward to it very much. And we've also got two Google Summer of Code students who are going to give a very tiny presentation after the Accelerate presentation. Dave Philly has been working using the Accelerate library, and Jesse has been working on something completely different, but we couldn't find a slot where it would fit in. So Jesse's going to do an introduction to what he's been working on, and we'll hear more about what he's been working on. Had we been able to put the stuff in from the afternoon in the morning, we would have heard the introduction to what was anyway. Great. So over to you, Trevor, I think. Unless should I say anything else? No. Okay, good.
Great. Thank you very much, Mike. And welcome to the first day of ICFP. And as Dominic said, the inaugural functional high performance and numerical computing workshop. So thank you for coming. And today I'd like to talk about my work on developing a functional programming language for high performance computing. And hopefully today I can maybe inspire you a little bit to do great work so that there will be many more iterations of this workshop in future years. So as you may know, for the last decade or so, virtually all of our processors have included multiple processing elements in them. So a standard desktop CPU, like the Ryzen 7, might have 8 cores. Your iPhone is this kind of 2-core processor with these 4 sort of lighter cores for lighter weight, more energy efficient tasks. And then we also have graphics cards, which have thousands of cores on them. So we have these behemoth processors in all of our computing devices these days. And so if we look at something like the GPU, the graphics processing units, this was originally designed to improve the performance of video games. And it's a specialized bit of hardware where its only goal in life, really, is to pump out as many pixels onto the screen as fast as it can. That is its goal in life. But as the demand for computing has increased over the last decade or so, we've seen scientists start to use these kinds of processors, which were originally designed for the most non-useful kind of workload you can imagine, playing video games. We're starting to see them to use in real scientific applications, right? We want to use them in things like machine learning, data science, computational physics and chemistry, medical information, medical imaging, bioinformatics, these kinds of really hard sciences. And so the reason that people are interested in using these things is because we've started to figure out ways to really leverage this specialized architecture to perform these more general tasks. And so we can get much higher performance on these tasks, which have thousands of cores in them, than we can on a traditional processor. However, this specialized hardware also comes with a specialized programming model. It's a different kind of hardware, so we need to program it in a different kind of way. And that's more challenging. It's more difficult to make efficient use of these processors. And so we have all of these extra complications to deal with. How do I sensibly deal with 2,000 threads working together on one problem? How do I manage that? How do I think about things like control flow, or how do I make the most efficient use of memory? So there's lots of extra additional complications to using hardware to use it efficiently. And so I want to try and illustrate that for you, to illustrate this problem for you. So you might hope that as you're developing your program, that the amount of effort you put into writing this software is somehow correlated to the amount of performance that you get out at the end. However, if you've ever tried to write a concurrent or parallel program, you'll know that you spend really a lot of time just staring at your program and figuring out, okay, where is the parallelism in this program? And so you stare and stare and stare for a really long time. Like, aha, I found it. And so you implement, and then on these 2,000 cores, you get this like tiny little speed increase. And like, oh, well, that's a little bit disappointing, right? So you keep staring at your program, you try really, 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 really hard, and then you figure out, it's like, okay, now I know how to use this specialized memory system. And so now you get a satisfying jump in performance, right? And you keep staring at your program, and then you figure out the next kind of hurdle or weird architecture quirk that you need to deal with. And this process sort of continues, right? And so for some people, they're quite happy to do this, right? To really spend a lot of effort to get the maximum amount of performance out of their program. But on the other hand, some people really care more about the performance per effort, or the productivity that they can get out of their programming language. Maybe we want to focus on our work on this side of the line. We want to focus on how do we maximize our productivity or our performance per effort. And so this really summarizes kind of the design, where I'm looking at when I think about high performance computing, staying above the line in this performance per effort ratio. And so there's a question of, where does this line continue, right? Does it continue indefinitely all the way to the end? Maybe. Or maybe, you've written your program and you've run your simulation and you have the result that you need already. And so you can just finish now. So maybe you didn't get the maximum performance out of your program, but you got enough to get the results you need, and now you can more quickly move on to the next problem. And so this is just sort of a very high-level illustration to give you the idea. It's very simplified. In reality, it probably looks a lot more like this. And you laugh, and that's good, but this is actually a real thing, right? So this is a quote from Jeff Larkin. He says, "After expressing the available parallelism, I often find the code has slowed down." And so Jeff, he works for NVIDIA, and this is a company that is selling this hardware that people are trying to use. He works for the Developer Technology Division, and he's talking about a programming model called OpenACC. So this is a thing that they developed to try and help people make better use of their hardware. And so if the people that are selling the hardware and designing the software to make you, to help you use it, say that, yes, this is very difficult, my programs often get slower, then in some ways the bar is both much lower and much higher at the same time. But the overall question remains the same, really. Can we have parallel programming with less effort? How do we stay above this productivity line? With, of course, the implied side condition that the resulting program should be fast. So the first part of this is, how do we design programs that are parallel? How do we think about parallel programs? So let's say I have a kind of standard C program. I have some kind of loop in C, and I want to do something in parallel. How do I parallelize this? Well, the POSIX Threads API was standardized in 1995, so I can use that API to spawn some threads to do work on all of my different cores and get a result. So in theory, that's all I need. But of course, in practice, it's very difficult to get these explicit threading models to work correctly. And so why is this difficult? So the problem comes from concurrency, right? We have all of these threads that are working at the same time concurrently, right? So I have multiple threads, and they're all executing at the same time, and all of their executions are kind of interleaved at the same time. And I don't know when one thread is going to be executing and when one is not, right? I don't know when exactly the threads are doing the work that they need to do. But at the same time, each thread has access to make effects in the world, right? A thread can write some value to global memory, just mutate state, as it were. Why would you do this kind of thing? So we have multiple interleavings of all of the threads, and all of the threads can make changes to the state of the world anytime they want. So we really have a lot of non-determinism in how our programs are being executed, and we need to kind of pay very close attention to how do we control this sort of concurrency. And so this is really where a lot of the problems come from. And then this idea, or this issue of dealing with non-determinism and concurrency is where a lot of the models like locks and semaphores and SKM come from. All of these methods to try and deal with these problems of non-determinism and concurrency. So, you know, if concurrency is very difficult, maybe we can simplify it a bit. Instead of having this completely unrestricted parallel model of concurrency, where we have lots of threads and they can do whatever they want at any time, let's simplify. So let's focus on this idea of data parallelism, a more restricted abstraction. So in data parallelism, the idea is conceptually simple. Instead of having lots of threads, each doing their own thing, now we have a single conceptual thread of control. We're just applying the same operation to lots of data at the same time. So this is very easy on the human brain to understand. There's a single conceptual thread of control. So this abstracts over the need for concurrency control, and it abstracts over the non-determinism. So we know that our result is deterministic. We have a single logical thread of execution because every thread is doing the same thing just on different data at the same time. So when I run my program, the results will be deterministic. Every time I run my program, I will get the same result deterministically. It's not going to matter on which order the threads happen to decide to run this time compared to the next. And it's also independent of the amount of parallelism that was actually realized, whether I ran with 2 threads or 1,000 threads or just 1. So it's a nice logically simple programming. So this is great for developers, it's nice and simple, but it's also great for the hardware because it matches what works well on the hardware. Processors are very good at working on chunks of data at once. They're not very good at working on single elements at a time. So if we think about our original C program, when I'm expressing that as a loop of single elements at a time, that's not the best way to make use of the hardware. Another advantage of data parallelism is, of course, energy efficiency. So if we have this simple logical thread of execution, we can really optimize our programs to maximize the amount of work we can do per unit energy. And so this has been one of the main advantages of these specialized GPU hardware. They're very good at doing lots of parallel work for relatively little energy. And we can do that by minimizing the amount of control logic that's required. We have a single logical thread of execution. And by maximizing data locality. We know how our data is being used by all of these threads at once. And so, we tend to think of data parallelism as parallelism over rectangular structures. So I have some kind of rectangular structure like an array, and I just want to apply the same operation to every element of the array. It's the classical view of data parallelism. But this model can really be pushed a lot further than that. So instead of just having a single flat data structure, if we have nested irregular arrays, then we can express more kinds of things. We can express computations over tree structures with this. And if we push the model a little bit further, then maybe we get into something like this amorphous data parallelism realm, where now our concurrent operations, they might conflict. New operations can be created dynamically, and they can modify the underlying data structure itself. So now we can start to do computations over things like graphs or mesh refinement algorithms. So given these various levels of expressiveness of data parallelism, we can start to classify them as a kind of taxonomy, where on the bottom axis we have expressiveness of computation moving to the right, and on the vertical axis, expressiveness of like how much parallelism can we deal with here. And this axis also goes like, I can express more things going up the axis, but it's also more difficult to implement those models. So this is the kind of design space taxonomy that we're thinking about. I've drawn this as nice sort of discrete boxes, but really this is sort of a continuous scale. So you just fall in a box somewhere. And then you can also think of a third axis coming out of the page where we can move from general hardware, general CPUs, to more specialized hardware, like our graphics processing units. And so we can start to classify what kinds of programs we can express in this data parallelism idea, and how we can do that. So my work is in this room. So I work primarily on this programming language called Accelerate. And so this kind of has a bit of a history. So before my time, there was a very ambitious project called Data Parallel Haskell, where they tried to parallelize all of Haskell. It was a wildly successful research project. It produced many great technologies, except for a data parallel compiler. But a lot of other cool reusable stuff. And so they thought, oh, well, okay, maybe we can turn it down a little bit. Let's try and do something easier. Like, let's slide down this scale of expressiveness and also ease of implementation. And I worked on the Wrapper project. And so my work, Accelerate, is in the same vein, right? It's in the same row of this taxonomy. But Accelerate is more focused on the out of the page access. Let's look at specialized hardware implementations. So a quick look at this embedded language Accelerate. So we have Accelerate, this embedded language, and embedded in Haskell. So when I'm writing a program in Accelerate, I'm really writing a Haskell program that generates an Accelerate program. And so when I run my Haskell/Accelerate program, what I'm really doing is, that I want to run on the GPU, what I'm really doing is, at runtime, my Haskell program is turning that Accelerate code into code for the GPU. It compiles it, runs it on the GPU, and then copies the results back. And so this kind of loop might happen many times within your program execution. And it's actually very similar to the original model for programming graphics cards. So shading languages like GLSL have a similar kind of loop where they do online compilation for the graphics shaders. So this is how games are written. So it's similar to the traditional GPU programming models, actually. What does it look like to program in this language? So the classic example in this array programming world is a vector dot product. So I want to write a dot product implementation in a very Haskell-like language. I'm using Haskell here. Haskell is our host language. X's and Y's here are my inputs. These are my two arrays that I have as input. And so the first thing I want to do is to pairwise multiply each element of the array. So I have one array of values here, X's, and a second array of values Y's, which I got from somewhere. And I just pairwise apply the multiplication operation between each of the elements. So this gives me the first part of the result. And then I can take that, and I need to sum all of those results. So I can use this operator fold to sum all of the results with the initial element of 0. Yeah. And so this is a kind of very canonical implementation of dot product in Haskell. And the only thing I've really left out here is the type signature. So if I include that, my program looks something like this. So I import the standard prelude, and my dot product program has this type signature. So given some type variable a, where a is a number, like a floating point number, that's a double precision number, give me a list of 2 lists of those numbers, and I will give you the final result in that. So this is the type signature for my implementation. But I also said that, well, these are lists, so that's a real linked list in Haskell, where I have a pointer to each element. So in terms of performance, that's obviously not very good. I have to follow a lot of pointers to get to every element. So a better way to implement this is to use an array. So if I instead import this library, data.vector.unboxed, then I get standard C-style arrays, where all of the values are lined up next to each other in memory. And so my type signature has changed a little bit. So I still have numbers, but I also need to have this unbox constraint. I need to know, how do I lay out all of these values in memory? But then given those constraints, I have a vector of those values, 2 vectors of those values, and I can get the result, right? And so my type signature has changed, but if you look at the implementation, that is still the same. The implementation here is still, well, I pairwise multiply each element of my array, and then I sum the results. I fold over the results. And so this is the approach we took with Accelerate. We wanted to build a programming language that would closely match what a Haskell programmer would be familiar with, if you squint at the types a little bit. Okay? So my type signature is, again, more complex. It expresses more things that I need to know in order to run my program on the graphics card. But the implementation is still the same. I still pairwise multiply each element and then fold over the result to get the final scalar result out. Right? So this language, this library, Accelerate, consists of a set of high-level combinators, like fold and zip with, that are designed to look a lot like the regular Haskell functions that a Haskell programmer would be familiar with. And so this is a simple programming model. Data parallelism is a conceptually simple programming model, but it is powerful enough to express some real-world problems and at a level of abstraction that still allows us to generate efficient code. So if we're thinking, like, how do we design programs that will operate efficiently in parallel? Right? So computers are good at operating on data in bulk. They're not good at operating on single elements at a time. So we need a language that would encourage working on data in bulk. Right? And so even low-level languages, systems languages like C, are not really good at this kind of thing. They still focus on operating on individual elements, not operating on data in a bulk. Right? And so here is some advantage that functional programming gives us. We're used to these kinds of combinators that express how do we operate on our structures in bulk rather than element-wise. And we can also design our language so that we can add restrictions that help guide the programmer into writing an efficient parallel program. If I only provide language features that I know how to compile efficiently, then the programmer is guided, forced, into writing an efficient parallel program. And so this is kind of a double-edged sword as well. Right? It's more restrictive in what the programmer can do, but if they can express it, the result will be efficient and execute in parallel on the hardware. So parallel programming and functional programming are a nice fit for this. the programming models of both kind of tie in well together. These ideas of operating on collections in bulk with combinators are a natural fit for parallel programming and just high performance computing in general, which match well to what the hardware expects. Okay. So we have a nice high level language or an idea about how to think about programs in parallel. How do we actually make it work? So, when I was much younger, when I was still a PhD student, and I was starting work on this, John Hughes came and visited our lab at the University of New South Wales in Sydney, Australia. So he came over from Chalmers. And I had the opportunity to speak to him one-on-one. And he asked a very simple question: what do you do? And if you've never met John, he's the nicest man ever. And he sat there very patiently and he listened as I kind of bumbled my way through this explanation of we have this kind of embedded language thing, and it operates on arrays, and well, we're trying to compile code to the GPU, and it wasn't a good explanation. Right? But what I learned from that is, rather than trying to tell John what I'm doing, I should show him. Right? So, after John left, so I wrote this little example program. So I think this was the first little example program. And so the code is very simple, and it's just for every pixel we have an x, y coordinate, and from that coordinate we can calculate the value of a sine and a cosine. And so you can calculate a few of those and sum them together, and you get these sort of nice interference patterns. So you can get these sort of repeating structures. And so if you do that, and then you kind of let time vary and let the angle vary, you get these nice patterns that emerge. These nice sort of emergent patterns come out of this very simple code. So the implementation, like the code to write this, is very short, maybe 20 lines of code, something. But actually making this work, like all of the machinery behind it, so that you can just go run and have a thing play, is really a lot of work. And but it really demonstrates quite vividly, what you're trying to achieve. And so from there, I went on with this idea and worked on larger programs. So this is another program that I wrote. So this is one of these mini apps, originally developed at Lawrence Livermore National Lab, one of the big supercomputing places in the US. And so what it is simulating shock hydrodynamics. So there's an explosion at the origin, and it simulates how the pressure wave propagates outwards through the medium. And so, Lawrence Livermore has a collection of what they call mini apps, which is designed to give you an idea of what your real simulation code is going to be like on their supercomputer. Right? At these levels, every supercomputer is designed differently to tackle different sorts of problems, and so you want to understand what kinds of code you should execute on each supercomputer. Right? So this was another example that I wrote, where I really learnt a lot about what it means to sort of implement these things, really using your language and trying to achieve something. Right? And so in the end, the performance is very good, right? So there are some reference implementations that come with this. So there's a C version that uses OpenMP for Parallelism, and there's also a CUDA version. And so there are a few thousand lines each, and if you run them, they take about a minute on the CPU and 5 seconds on the GPU. And then the Accelerate version is actually much more concise. It's a much higher level description, it's much shorter in terms of lines of code, but in the end we actually managed to get faster runtimes out of it. And then when we wanted to port this to the GPU, instead of having to completely rewrite it from scratch, really I just had to change one line and got very good performance out at the end. Right? So it's a nice, concise definition that uses these collective operations rather than explicit loops. And from that, the compiler really has enough information to generate efficient code. But these are the final results. When I first ran this implementation was at least twice as slow as this, maybe 10 times. I don't know, I can't remember. It's actually very difficult to try and rerun code that's that old. But just by having this nice high-level description, by successfully improving the compiler implementation without changing the actual implementation of the simulation code at all, then we can get down to an actual efficient implementation. So yeah, the initial version was actually quite slow, but just through that description still has enough information in it that an efficient compiler can generate good code from it. Okay. So here's another simulation. So this is simulation of water flow over a creek bed. So as the water flows over the sand, it starts to sort of wear away at different points and then generate these little channels. So as the water flows, sort of gouges channels to the sand, and then the sediment builds up on each side of the channel. And so you get these nice little sort of rivers that form naturally through this. So this might be simulating what happens at the mouth of a large river, for example. So we want to figure out where is the soil being eroded, for example. And so this was another example where we had some initial implementation in Python and OpenCL, which were written by the scientists initially. And then we tried to implement it in Accelerate. And we see the same kind of pattern. So actually the implementation is significantly faster, at least at that end of the scale, while also being more concise. So I think the takeaway here is really using real examples as a working laboratory to figure out what is working with the language, what needs to be improved. And so I think having these sorts of motivating examples has been very successful for Accelerate. You get to really validate and test your ideas, see how far your ideas can really go. If you have a great new idea for implementing a data parallel language, and dot product works really well, but that's the extent of what you can express, then you need to figure that out, right? And you can only do that by trying to work on larger example programs. You can use that as real motivators to improve performance, like I did with the Lulash program. And this is one of the problems that we also found with these initial projects, Data Parallel, Haskell, and Repo. They worked very well for smaller programs, but as you scale up to larger and more complex things, then things sort of start to fall apart. So scaling up to real example, like to larger example programs, I think tells you a lot about how your system works and what kinds of things you need to look at, focus on if you want to improve. It's also a good test bed to really test various things, like how can I improve the code generation to get faster code out of that? And so you learn a lot of surprising things by doing that. So at a first approximation, Accelerate tries to generate code that a human would write, approximately. But of course, humans are lazy and they take shortcuts. And so this is why we can actually get better than handwritten code. Our compiler can be not lazy and generate the kinds of code that everyone knows they should write. It is actually very tedious and difficult. And other interesting things, like a standard C program will use a lot of in-place updating, but actually that doesn't really affect performance much at all. So you can learn a lot of interesting things by looking at real example programs to find out what's actually important to work with. And so writing larger programs as well, you learn what is good about your language, what is bad about it. So I learned a lot of kind of ergonomics problems. writing larger programs in Accelerate. Things that aren't annoying when you write small programs, they get more frustrating as you try and write 100,000 line and more programs. So that gives you an idea of what needs to be changed, what needs to improve. And so, yeah, having motivating examples I think tells you a lot. And so you can take what you learn, you can look at what's good about whatever you're working on, and presumably you find it interesting. Something is interesting about that work that you're working on, otherwise you wouldn't do it. Even if you're not really sure yet what that interesting bit is, but you can kind of look at that and take it and use it as a seed to make that better and improve on your work. So I think having motivating real examples has really helped the Accelerate project move forward in good ways. So the third part, what's next? So where do we go from here? And so this is partly future work for Accelerate, and partly sort of speculation about what the community can do moving forward. So in software engineering, we tend to have this idea of that we can tame complexity by climbing the tower of abstraction. Right? We just have an ever-increasing sequence of abstractions over our models, and that build upon each other. And then by having more abstractions and more layers in this model, then we can just tame all kinds of complexity in our program. And so programmers have gone through this sequence of abstractions over the years. Right? We used to program our computers using machine language, and then we wrote assembly, and then we moved on to high-level abstractions. Right? Fortran, C, C++, and then managed languages, C#, Haskell, JavaScript, that kind of thing. And yes, it does pain me to put these on the same line. And so the justification for this is always that, I'm working at a higher level of abstraction. I'm being more productive, right? Being smart, saving effort. And that is true. I'm not saying that everyone should go program in assembly. But I think it's important to point out, especially for this crowd, like focused on high performance computing, that somewhere along the line here, I feel like this went a little bit wrong. And this is how all things kind of go wrong. You start at a good place and then you extrapolate into wrong territory. So, where did this go wrong? So, here are a few examples. So, this is a program in Haskell, right? I give it a list of double precision numbers. And so I can calculate the sum of those numbers and then divide by the length to compute the mean. Right? So, what does this program compute? Yeah? What does this program do? And the answer is, it generates a space link. Because this program should really run very quickly in a constant amount of memory. But actually, it consumes 70 or 80 megabytes of memory, and takes a really long time to execute. Right? And this is not obvious. Right? We started with a nice high-level abstraction about what I wanted to compute, but the actual performance implementation was very different from what I expected. Right? It was surprising. Here's another example. So let's say I have this data declaration in Haskell. What does this look like in memory? Yeah? How is this laid out in memory? So if you dig in the GHC documentation, you'll find out that it looks like this. I have some header for my constructor, and then I have 2 pointers to the fields. And so on the heap somewhere, I have another 2 constructors, and then the actual value. And so the common wisdom is to say, well, you can remove these indirections by unpacking the int directly into the constructor. Right? And so now I have this much more efficient, compact in-memory representation. I don't have to follow these 2 pointers to get to my actual values every time. But that's surprising, maybe. Here's another example. Can I do the same thing? I have a data constructor, and I want to have 4 word 8s, so single byte values in that packed together. So So let's say I'm working on some kind of video processing algorithm and I want to use the simmed instructions, where I have 1 byte for each of my red, green, blue alpha channels. Right? And I really want to access the simmed instructions using this value, right? How much memory does this consume? You know, I've learned from my previous mistake, and I've unboxed all the words, so everything should be in memory. But actually in Haskell, there's no such thing as a word A. Everything is a full machine word. So the size of this thing is actually much larger than you expect. Okay? So, surprising. Here's another example. Let's say I have this data type, polymorphic data type. So what happens if I want to know whether or not this value has been computed? How do I do that in Haskell? Now, Haskell is a lazy language, and it's only going to evaluate this A when it's actually demanded. Right? But how do I know that? How can I test, has this been evaluated yet or not? And so if you look on Stack Overflow, you'll probably find a solution like this. You know, well, you can put the value, you know, maybe, and put that in a mutable reference. And so now I can update this reference and say whether or not I have it. But then if you look at, you know, how is that laid out in memory? Well, this is much more complex now. I have my header, and then this points to an IRF, and then this points to either the nothing or the just case, and then if I have the thing, that can point to the value. Okay? And you can do the same trick, and you can unpack the reference into this constructor, and you can save one indirection. And sure, that's good, but it's kind of beside the point, because all of these other things are still lazily evaluated, and that's exactly the thing that I wanted to avoid, right? The Haskell runtime system already knows whether or not this has been evaluated, but because I've completely abstracted that away, and I have no access to it anymore, it's very difficult to get that information. So we usually only talk about one side of this abstraction, right? But there's another side, right? So we like to say that we're being smart and we're saving time, but we don't see that there's a corresponding loss of capability. Yeah? Because I don't program in assembly anymore, I don't know how to program in assembly. Because I use managed languages, I don't know how my memory is laid out, where variables lie in memory. I certainly don't know what the CPU is doing in response to the code that I write. And so the rhetoric here is, you know, I'm being smart, I shouldn't have to do the low-level stuff. But the reality is also that there's a loss of capability that corresponds to these choices that we make in our abstractions. And both of these things can be true at the same time. Maybe you don't have to, maybe you shouldn't have to do this, but if you want to, if you really need to get that last bit of performance out of your program, are you able to access these capabilities? So complexity really works in both ways. So if we go back to this diagram, and we had this picture, you know, how do we make it a functional high-performance computing language? How do we make this line go all the way up to the maximum performance area? And so the title of my talk was really a pun. It's talking about a functional programming language, but it's also really talking about how do we make high-performance languages that are functional, that are practical, and that are useful. Right? So even if I'm working at a high level, sometimes I really need to know how all of the low-level stuff works as well, and have access to that to really get good performance. And so I think, yeah, having real-world examples to develop these things and work on these has been very important to test out new features, test performance, improve the language as a whole. So real examples are very useful to have. And what is a real example is going to depend, it's going to be different for each of your domains. And knowing that working at a high level is good, I'm not saying everyone program in C, program in assembly, that's terrible. But just understand that this also entails a loss of capability. And, you know, even though we're working at a high level, the reality is that all of this code is executed on the machine, and that's a very low-level thing. So, functional programming languages, I think, provide the right set of abstractions so that we can make very good use of this hardware. But I think we just have to be a little bit cautious in this particular crowd when we're thinking about how do we get very high-performance functional programming languages. And so instead of just thinking, you know, let's just continually climb this tower of abstraction, it's a very abstract, high-level things, maybe a better way of thinking about this is, well, let's keep our feet on the ground with the low-level hardware stuff as we reach for these higher-level abstractions. Okay, thank you.
Great, thanks very much, Trevor. Questions?
First of all, it's an extremely interesting talk, and what is so great to see is how you've actually implemented these practical examples. So I want to ask you kind of a very open-ended question. When you described a little bit about Accelerate working in the various applied programs, you said it's still based on efficient work with arrays and dot products and that sort of thing. And it took like 1,000 lines to maybe put that example back together in Accelerate. What do you think would happen if you looked at a completely different language that is extremely close to the mathematics? So this, like the language used by Mathematica, because the problem could actually be formulated in a few lines there, like 10 or 20 lines. And Mathematica, for example, has the ability to already do the discretization and all these kind of things. And you sort of wonder if there is something special coming down from the mathematics problem that influences the parallelism.
Yes.
And so, because for example, the geometrical layout of the data is encoded in the mathematical formulation, but is lost at the level of arrays. Yeah, if you reorganized your arrays, you would get terrible performance.
Yeah.
And the only way it works right is because it was connected to physics in one way or another. So what would the really big picture look for parallelism if you go from math to this specialized code? What do you think about that?
I think that can vary. So given your particular problems, like it's known how to discretize a PDE and solve that. And so that kind of extremely high level approach works. So like we know how to do that. I'm not sure we know how to do that for all kinds of problems. So I guess this example in particular, Lulesh, there is an analytical solution. So you could do that, you would have the mathematics. But for the general code that it's simulating, it's a much smaller part of that. So I don't know, like Lulesh models this tiny part, the explicit hydrodynamics part. I'm not sure if that idea of just taking the equations extends to all of these other parts, or whether you still need some level of explicit control about what you're doing. I'm not sure how that would work.
But let's just focus on the little box where Lulesh works. What influence does the mathematical and physical origin have on the data organization?
I mean, okay, to be honest, I don't understand the physics. I was given the reference code, I'm like, okay, implement this. So there could be a better way to do it as well, but I don't know.
So, when you're expressing these computations with the folds and those equations and stuff like that, do you build up some kind of call graph under the hood and then do some kind of like whole program generation of the CUDA kernels or whatever, or do they kind of?
Yeah. So I didn't talk about it. So ACC here is actually just a data structure. So exactly like you said. So as you're writing these programs in this style, you're actually just building a data structure. And so when you say, okay, run my program now, you get this whole call graph, and then it takes that and generates code from that.
Does it just do one CUDA kernel from it? Like,
No, you'll have like a large sequence of kernels, yeah.
Hi. So in the first part of the talk, you mentioned an evolution from data parallel Haskell to REPA to accelerate. So what were the kind of shortcomings that you faced in data parallel Haskell, which approach becomes
So this is sort of work before my time, but part of the same group that I joined. So I'll try and give you my perspective, but if not, I can point to the people in the room who actually did that. So Haskell is a very complex language, like it's very expressive. So actually being able to completely parallelize the entire language is very difficult, essentially, right? And so there was a lot of work done in trying to improve that, and it did work to a point. And then similarly for REPA, which takes a simplified model, right? It works to a point, but remember that GHC, the Haskell compiler, is an excellent Haskell compiler. It's a terrible Fortran compiler, okay? And this kind of code, this numeric loopy style code, is really not what it's designed to do. So they were very ambitious in these projects. Take all of Haskell, try and parallelize it, and let's compare that to the performance of a C program. So it was a very challenging project. So I would still say it's successful, even though DPH doesn't exist. A lot of great stuff still came out of it.
Do you have a long-term goal to migrate accelerate upwards here?
Yes. The long-term goal is to move upwards here, to be able to improve the expressiveness of what kinds of parallel programs you can express.
Have you got some examples that are kind of pulling you upwards?
Yes. So in this simulation code, as you scale that out to a larger area, so if you want to simulate an entire river system, that just becomes a lot of data. So you need to start looking at irregular structures and adaptive meshes here. So for areas that aren't changing much, you can just have that very coarsely represented, and then where we have things that are changing very rapidly, we have a much finer representation. So this kind of example is driving that sort of irregular adaptive mesh refinement work. So we've just started looking in that area.
Going back to your other slide with the, and you mentioned the third axis coming up this way. Are there any projects working in that direction?
Yes, so that was the original goal of Accelerate, to work on how do we program for specialized hardware like GPUs.
Yep.
So this supports GPUs as well as the multiple CPUs. And so that can extend out further to like more specialized hardware like the Xeon Phi, which is dead now, though, or like distributed systems over clusters. So we are currently single node, but you could expand out over clusters, for example.
There's a lot of people working on strange hardware out in California too.
Yes, other
GPUs on machine learning.
tensor processing things for deep learning, that kind of thing.
For example, yeah.
Because our programs are really just data structure, like we were discussing previous question. You can take that data structure and feed it to a different compiler, essentially generate code for a different target architecture. It really is a just-in-time cross-compiler.
Any other questions? Good. Okay. Thanks very much.
Okay.